So in the last lecture, we looked at merge sort and we informally claimed that it was much more efficient than insertion sort or selection sort. And we claimed also that it operates in time order n log n. So recall that merge sort has at its base a merging algorithm which takes two sorted lists A and B and combines them one at a time by doing a scan over all elements. So in order to analyze merge sort, the first thing we need to do is to give an analysis of the merge function itself. How much time does merge take in terms of the input sizes of the two lists A and B? So suppose A has m elements and B has n elements, and we want to put all these elements together into a single sorted list in C. Remember that we had an iteration where in each step of the iteration we looked at the first element in A and B and moved the smaller of the two to C. So clearly C grows by one element with each iteration, and since we have to move all m plus n elements from A and B to C, the size of C is m plus n. Right? What do we do in each iteration? Well, we do a comparison and then we do an assignment and then we increment some indices. So this is a fixed number of operations, so it's a constant. So the total amount of work is proportional to m plus n. Now notice that m plus n is at most twice the maximum of m plus n. Right? So if m is 7 and n is 15, then 5 plus 7 plus 15 will be less than 2 times 15. So we can say that merge as a function takes time of the order of maximum of m and n. And in particular, very often, like in merge sort, we are taking two lists of roughly the same size, right? We divide a list into two halves and then we merge them. So if both m and n are of the same, approximately the same size, then the max of m and n is just one of them, n itself. So essentially, merge is linear in the size of the input list. Now, having analyzed merge, let's look at merge sort. So merge sort says that if a list is small, it has 0 or 1 elements, nothing is to be done. Otherwise, you have to solve the problem for two half lists and then merge them. As with any recursive function, we have to describe the time taken by such a function in terms of a recurrence. So let us assume for now, since we are going to keep dividing by 2, that we can keep dividing by 2 without hitting an odd number in between. So let's assume that the input n is some perfect power of 2. Its n is 2 to the k. When we break up merge sort into two lists, we have two lists of size n by 2. So the time taken for n elements is 2 times the time taken for two lists of n by 2, and this is the merge component. We have an order n step which requires us to merge the two lists of size n by 2, and remember we just said that merge is linear in the size of the input. So we have two subproblems of size n by 2, that is the 2 times n by 2, and we have merging which requires order n. So as with binary search and with recursive insertion sort, we can solve this recurrence by unwinding it. So we start with the base case. If we have a list of size 1, then we have nothing to do. So t of 1 is 1. And t of n in general is 2 times tn by 2 plus n. So if we expand this out, so we substitute for tn by 2, we get 2 times tn by 4 plus n by 2, because that if we take this as the new input, this expands using the same definition. And if we rewrite this, so we write 2 times 2 as 2 squared, and we write this 4 as 2 squared, we will find that this is equivalent to writing it in this form, 2 into 2, 2 squared, t n by 2 squared. And now notice that you have 2 times n by 2 over here, right? So this 2 and this 2 will cancel, so you have one factor of n and another factor of n. So the important thing is that you have a 2 here in the exponent and you have a 2 here before the n. Now likewise, what we will do in the next step is to expand this 2 times tn by 4. So we expand 2 times tn by 4, that will give us another n by 8, which we write as n2 cubed. And this, which used to be 2 squared, 2n by 2 squared plus 2n, will turn out to be 2 cubed, 2n by 2 cubed plus 3n. So notice that the 2's have become 3's uniformly. So in this way, if we keep going After k steps or j steps, we'll have 2 to the j times t n by 2 to the j plus j times n. Now, how long do we keep doing this? We keep doing this till we hit the base case. So when j is log of n, where log by log we usually mean log to the base 2, then n by 2 to the j will be 1, and so t of n by 2 to the j will also be 1. So after log n steps, this expression simplifies to 2 to the log n plus log n times n. Everywhere we have a j, we put a log n, and take this has become 1, and so it has disappeared. So we have 2 to the j, which is 2 to the log n, plus this j is log n, and then we have an n. And this is 2 to the log n by definition is just n. So 2 to the log n is n, and we have n log n. And by our rule that we keep the higher term when we do big O, n log n is bigger than n. So we get a final value of O n log n for merge sort. Merge turns out to be a very useful operation. What we saw was to combine two lists faithfully into a single sorted list. In particular, in our list, if we had duplicates, if we merge say 1, 3 and 2, 3, then we end up with a list of the form 1, 2, 3, 3. So this is how merge would work. It doesn't lose any information. It keeps duplicates and faithfully copies them to the final list. On the other hand, we might want to have a situation where we want the union. We don't want to keep multiple copies. We want to only keep one copy. So in the union case, here is what we would do. So let us assume that we have two lists, and in general we could have already duplicates within the list. So let's suppose that we have 1, 2, 2, 6 and 2, 3, 5. Then we do the normal merge, so we move 1 here, and now when we hit two elements which are equal, right, then we need to basically scan till we finish this equal thing and copy one copy of it, and then finally we'll put 3 and then 5 and then 6, right? So when a and ai is equal to bj, we increment both sides and make sure that we go to the end of that block. The other option is to do intersection. So supposing we want to take 1, 2, 6 and 2, 6, 8 and come out with the answer 2, 6 as the common elements. Then if one side is smaller than the other side, we can skip that element because it's not there in both lists. So if ai is less than bj, we increment I. If bj is less than ai, we increment j. And if they're equal, we'd like union, we keep one copy of the common element. So merge can be used to implement various combination operations on lists. It can be used to take the union of two lists and discard duplicates. It can be used to take the intersection of two lists. And finally, as an exercise to test that you understand it, see if you can use merge to do list difference. So list difference is the following operation. If I have say 1, 2, 3, 6 and I have 2, 4, 6, 8, then list difference is all the elements in the first list which are not there in the second list. So 2 is there here and it is here, so you remove 2. 6 is there here and it's here, so remove 2. 6, so you should get 1, 3. So if this is A and this is B, then this is the so-called list difference A minus B. So see if you can write a version of merge which gives you all the elements in A which are not also in B, also known as list difference. So merge sort is clearly superior to insertion sort and selection sort because it is ordered n log n and can handle lists as we saw of size 100,000 as opposed to a few thousand. But it doesn't mean that merge sort does not have limitations. One of the limitations of merge sort is that we are forced to create a new array every time we merge two lists. There is no obvious way to efficiently merge two lists without creating a new list. So there is a penalty in terms of extra storage. We have to double the space that we use when we start with a list and we want to sort it using merge sort. The other problem with merge sort is that it is inherently recursive. Right? So merge sort calls itself on the first half and the second half. Now this is conceptually very nice. We saw that recursive functions are very naturally related to inductive definitions, and they help us to understand the structure of a problem in terms of smaller problems at the same time. Now, unfortunately, a recursive call in a programming language involves suspending the current function doing a new computation, and then restoring the values that we had suspended for the current function. So if we currently had values for local names like I, j, k, we have to store them somewhere and then retrieve them and continue with the old values when the recursive call is done. So this requires a certain amount of extra work. So recursive calls and returns turn out to be expensive on their own time-wise. So it would be nice if we could have both the order n log n behavior of merge sort, and we could do away with this recursive thing. But this is only a minor comment. But conceptually, merge sort is the basic order n log n sorting algorithm, and it's very useful to know because it plays a role in many other things indirectly or directly.